Yeah, let me introduce. So the next speaker is Sergey Borisenko from Institute of Solid State Physics at Dresden. So, okay, I think that the title is a bit adopted. Okay, the role of A in ARPES, and please, okay, the virtual floor is yours, Sergey. Thank you.
Thank you, Chairman. First of all, I would like to thank all Ukrainians for hosting scientific workshops while resisting and protecting our safe life here. And I'm grateful to the organizers, to Jeroen, Bernd, Sylvia, and others, Sasha, who made it possible. And finally, my deepest respect to Jeroen, Flavio, Maya, and Asla, who went there directly from the safe places to support Ukrainians. I do apologize for changing the title, but I heard a lot of nice presentations, and I thought since ARPES has been mentioned many times, I probably show you what was the life from our side in this direction many years back. This is 2017, I think, was very pre-ultramagnetism time. And I thought I mentioned this material, probably you find it also interesting. It's not an ultramagnet, but I think there are many interesting common features with it. So this is the iridium bismuth selenide. At that time, the mixture of probably the most fashionable atoms. And they are not magnetic per se, but they could be magnetic. In this material, they're not magnetic. So that's why it is not an ultramagnet. And in addition, it has got a center of inversion. But the very interesting feature, why we called it unusual semiconductor, is that we realized that there is a very huge splitting with at that time we called it gigantic Dresselhaus splitting as sort of 0.3 electron volts. And for us, it was very important because this fully spin polarized band was nearly touching the Fermi level. So this is a semiconductor, but a tiny doping would make it a metal, and one could get extremely interesting Fermi surfaces, and I'm going to show you what this is. So the resistivity, as you see, does not depend on magnetic field a lot, and the samples were very nicely characterized in Princeton. The ARPES data from semiconductors are usually not very spectacular because there is an energy gap, and in this particular case, the density of the Fermi level was relatively not very low, let's say, but nevertheless, one could still find the parallels with the band structure calculations. One could see that there are spots, what we call the remnant Fermi surfaces, very nicely reproduced in a large area map. And even the band structure was looking sort of approximately the same, but similar. But we became convinced that what we see in theory is observed experimentally when we zoomed into the gamma and gamma direction, and we directly determined those gaps, those bands which are strongly spin-orbit split and have extremely interesting spin character. So this is shown here as parallel here as for the spins parallel to momentum, and perpendicular is perpendicular to the momentum. As you can see, these bands are fully spin polarized, and interestingly, this is the evidence for the 3D spin momentum locking, because this feature exists along the gamma direction, gamma M direction only, which is making unique this remnant Fermi surface, point-like Fermi surfaces with a very well-defined spin character, which is always perpendicular to the momentum. So we thought this could be a very exciting material, and this is the summary of what we thought could be potential applications, is that it could be a source of a spin polarized electrons if one would use a circularly polarized light, and at the different angles we would get a spin polarized current. This is how the Fermi surface looks like. Do you see the mouse I'm pointing on this? Do you see my mouse on the screen?
Yes.
Okay, thank you. So these are these point-like remnant Fermi surfaces at a very tiny doping level. So one would have 12 of those. And as I said, with a very well-defined spin character. So here I try to show that this is the spin is always perpendicular to the momentum. So we have in reciprocal space a unique spin textured point-like set of Fermi surfaces with which have a spin chirality if one looks along 111, and one has, if one compares in the opposite direction, there is a certain spin chirality here. At this, the material is non-magnetic. At this, there is no net magnetization, and but I thought it is in the spirit of ultramagnetism, where you have spin splitting in the reciprocal space, but you do not have net magnetization, and the material remains non-magnetic. We also noticed that this could be this nice material with absence of the backscattering, because there is hardly any mechanism here, and possible there could be electric field controlled spin polarized current, because again, if we apply electric field, one would see that the rest would be compensated, and these two components would give us the spin polarized current. And we had a lot of discussions with theorists about the possible superconducting state, which, and especially after yesterday's talk of Oslo's, I remembered all those discussions. This was long ago, but perhaps this would be interesting. So again, this is not an ultramagnet in this, in any sense, because it has no inversion symmetry and it is non-magnetic, but it has this spin split electronic structure in reciprocal space. So we have, we call it giant ball-type Dresselhaus splitting. We managed to publish it a bit later because at that time it was not so fashionable. And I just show you that the terminology non-magnetic half metal, which at that time seemed to like oxymoron, in this case, I think is justified. And I just wanted maybe to hear your opinion, especially about the possible superconducting state, because we have this could be dependent on doping. The pairing could occur within the Fermi surfaces, or if the doping is very small, as I said, and the electrons from opposite Fermi surfaces will pair. So I think the superconducting state would be very interesting. Good, so that was the iridium bismuth-selenide, which we called non-magnetic half metal. And now I switch to more technical things. Why do I want to talk about the technical things? Because it's not too technical things, as you will see. It is a very simple thing, but there is another similarity to ultramagnetism. As we heard from the previous talk, or in other talks during this meeting, this question has been addressed a couple of times, why people didn't realize earlier that this is the case. So I'm encountered this situation a couple of times already in my scientific career, so there is no surprises. One should just go ahead and suggest them. And then people will, there are curious things which happen, which protect humanity to see certain obvious things. This one is technical, but again, ARPES is a technique which is very simple per se, but what I believe is given to the audience a bit too complicated. And the ARPES has been mentioned many times during the conference. It is indeed a useful method. Unfortunately for ultramagnetism, we realized after we saw that splitting's already seen, and this is something which is a more or less direct task for ARPES, so it's very hard to compete in this area. Let's come back to the A in ARPES. If you type in Google angular distribution, you will always, you can check it right now, you will find that there is a very, the most common image associated with this is the image in polar plot. Color image shows the intensity, for instance, the intensity of the particles into the half space should be shown. It's always a sort of circular polar plots with angles, and unfortunately, and surprisingly, in the case of angle resolved photo emission, if you type in ARPES in your search engine, you will see something like this. You will see the Cartesian plot with two variables named binding energy and momentum. And then you will see some sketch of an extremely complicated equipment. This you can check anytime. Another thing is that nearly every ARPES paper, and I showed you a couple of slides back, the same situation, the ARPES data are directly, this Cartesian plot is directly compared to DFT result with the band structure, with a high symmetry point, sometimes even overlapped, and in many cases, they do agree very nicely. Another thing is that another very often compared data set is the Fermi surface map, which is compared to the constant KZ cut. There's a Fermi surface, one cuts the Fermi surface at a particular momentum and compares with ARPES data, and this is usually taken for granted. So ARPES is a good method to measure intensity distribution as a function of binding energy and three-dimensional momentum. I show you some kind of couple of shocking statements, which were also interesting for myself. And one can, of course, always add strictly speaking, but I will show you that indeed these statements are correct. And in particular, it is not possible to probe any high symmetry direction of the brilliance zone, for instance. It is this widely accepted unit of information, if you see always on the screen, momentum versus binding energy, is actually a non-trivial data set, which is excerpt from the four-dimensional space, and it cannot be regarded as intensity versus binding energy and momentum along any line in the brilliance zone. And finally, it is not possible to probe energy distribution corresponding to a single K point. Because if you can check it yourself, the very famous tutorials show, okay, ARPES is an extent, you know XPS? XPS is energy distribution. So ARPES is an extension of XPS. It's the same just for every K point, so which is not correct. And this is the topic which I want to discuss with you and how to avoid this confusion. So the energy distribution curve is a confusing term because every K point is probed exactly once at one energy. So this follows from the very simple kinematics of the method. There is a lot of theoretical work to photo emission process itself, but this is out of scope of this presentation. I just touch only on kinematics and the simple kinematics of the method. And in our we define term angle resolved photo emission spectroscopy and its simple version as counting electrons as a function of photon energy, two angles, kinetic energy, that's it, 4 variables. In order to define dimension, in order to define direction in 3-dimensional space, you need only 2 angles. So these are these 2 angles. We call them theta and phi, and they will play the central role. As you see here, there is nothing quadratic. There is everything is cylindrical, taking into account that the lenses of the analyzers are cylindrical. So this is the simple sketch, and every tutorial starts with this angles. But then the people switch to other things. And this is the very simple conservation law, which shows that the kinetic energy of the photoelectrons is related to the energy in the crystal in a very simple form. So the simplest approximation, I took it from the very old photo emission work. And from this directly followed the main equations of the method, which allows us to relate these measurables, kinetic energy, angles, photon energy, with elements of the K omega space, as we called it once, or K binding energy space. So there's 4-dimensional space. And when you closely look at these very simple formulas, one could immediately realize that if we fix kinetic energy of the photoelectron, simple thing, we just measure only photoelectrons with the simple kinetic energies, we will immediately see that they will correspond to the sphere in the reciprocal space. When we are talking about the spheres in reciprocal space, one could, of course, mention immediately Ewald sphere springs to mind, and Ewald himself called this reflection sphere. In certain analogy to this, we will call it emission sphere. The radius of this emission sphere is also straightforward. You could see it directly from here. And it means that only the portion of the K space becomes accessible which sits on top of the sphere. This is the traditional, what I call now E approach, energy approach to ARPES. So here I show the typical data sets which are projected to the probed portions of this four-dimensional K-omega space. And starting from the very beginning, this is the energy distribution curve, which you probably remember from the old day photoemission spectroscopy as a chemical analysis tool with the peaks, which is excellent tool showing which elements inside. But as soon as we are talking about the angle result photoemission spectroscopy, this curve starts to have limited physical meaning in the sense that it doesn't correspond exactly only to energy. Because, as I said, kinetic energy changes all components of the momentum. It does correspond also to the momentum distribution. So the term energy distribution curve is actually not correct in this sense. It should be energy momentum distribution curve, just because when we start the spectrum at certain kinetic energy, then we go to lower kinetic energies, we arrive at a completely different momentum in the reciprocal space. Because of the angle multiplexing analyzes, not a single energy distribution curve is typically detected, but it is the whole range of these curves is detected. And this is why the ARPES made revolutionary steps, something like 20, 25 years back, because it was possible to record those with a very high angular resolution. This is a great achievement. Again, I will call it a rainbow plot, just because the portion in the K space, you see, is the what we call diff sector. We didn't find in the literature the proper name for this portion of a circle or a sphere, but it reminds us the difference between sectors of circles with different radii. So I call it rainbow plot just because the area in K space reminds the rainbow. And what is more important, every arc corresponds to different binding energy. Finally, if you have a possibility to scan another angle, then one could do what I call ARPES union if one measures the whole angular space and kinetic energy. In this case, one gets this data set. One often believes this is everything, but this is a very tiny portion of the information which can be obtained from angle result photoemission spectroscopy. The very top of this, if the rest is thrown out, is a very useful thing. This is indeed momentum distribution on the emission sphere in the K space. So we call this one a spherical diff sector, and the top will be 2D Fermi surface map. How significant this effect is, maybe it's just something not very relevant. I tried many different materials. We have a lot of band structure calculations from Sasha Ereska, so we enjoy navigating through them for many different materials. This is one of the examples. I've worked with titanium detelluride, but with switch, this is very fashionable material now with the Institute. So this is platinum bismuth too. And if you look at data set, this is a Fermi surface cut at a fixed KZ. And you see this is a repeating zone scheme, and you see the Fermi surfaces which look different, which look the same when you go to the higher momentum value. And this is the data set which is reconstructed from this, from the band structure calculations. So this is the cut of this Fermi surface by the sphere. And this is what ARPES experiment should see. Okay, so first you understood that you see that the difference could be quite significant. Now, but still, this is sort of visual thing. One could understand, okay, this is sphere, and this is what is sometimes discussed in ARPES paper, that we are not cutting like this. If you saw H nu dependencies. The sphere is often shown, but let's have a look what else is in this. So if we consider the Fermi surface cut, this is more simple thing, this is more visual, it's understandable. Let's now consider the cut along this momentum, along Ky, and see how the band structure looks like. So this is a typical band structure, just from the band structure calculations along the high symmetry direction, binding energy, Ky. And this is the reconstructed rainbow plot from the band structure calculations. This is what we're supposed to see in ARPES if I say, okay, here's the band structure along this high symmetry direction. As you see, there are hardly any similarities between these two data sets, except of perhaps here near zero, at very low energies, at very low angles, at very low momentum, there is a certain correspondence. You can look at the map, there is a certain correspondence when you stay close to the gamma. And this inset actually shows why this is so, because the blue arrow corresponds to this. This is now view from the side. This is a photo emission thing. People draw such Ky, Kz plots very often to find out where V0 is, where this inner potential, where they cut the momentum space. So this is one of those. But here, in addition, I plotted again the rainbow. So this is the portion of the K space which is probed in the typical photo emission experiment in E approach. And this is the band structure calculation. So as this plot implies, so we start from the gamma point, and then we go along Ky, Kz, in this case, Kx is 0, and then as a function of Kz, we can move in this direction. So one could see from this plot that as soon as magenta line is close to this blue line here, then everything is fine. So you can work in this approximation, meaning low binding energies, small momentum. Then but nevertheless, every kinetic energy corresponds to different momentum. So one has to take this into account when one considers band renormalizations like Latinger current, some of the macroscopic things in photo emission in ARPES, which are usually considered. All this is really influenced by that. A quick estimate is typical irreducible part of the Brillouin zone is 0.5 reciprocal angstroms. If one measures with a helium-1 radiation, 21.2 eV, and records the spectrum down to 5 eV, sometimes people record down to 10 eV, then by 5 eV binding energy, you go through a reducible part 2 times. So this is indeed a strong effect and has to be taken into account, especially if the material is pronouncedly three-dimensional. So what to do? One could look at this plot here and take materials with smaller lattice constants. Smaller lattice constants, larger the Brillouin zone. Larger the Brillouin zone, we cover less portion of the Brillouin zone. One could find the materials with larger inner potential. Happen to be that some material, the V0 can derive from 5 to 20, as far as I know. One could go to higher photon energies in order to increase the radius of the emission sphere. And then it's tangential to it would be kind of emission sphere. One could live with this, but then one loses energy and momentum resolution. One could go to smaller emission angles and measure just near the gamma point. Wow, no, very interesting. Or one can consider very small energy range. Of course, if we are staying close to the Fermi level, 100 millielectron volts or so, to determine superconducting gaps, renormalization, Fermi velocities, self-energy effects, this is fine. 100 millieV, it's less than a very, very small fraction of the Brillouin zone. One can neglect it, and one could do this. But as soon as you see the plot, which shows everything with the band structure, one has to be cautious. What to do? A approach. A stays in ARPES for angle, and A approach is trivial. One considers angle first of all. This reminds me of some other slogans, but anyway, so angle, if we consider this curve is momentum distribution curve. It is angular distribution curve, but it is translated to momentum like momentum distribution curve. And it has a very transparent physical meaning. It is indeed intensity distribution in the K space sitting on this emission sphere. When one does what we call theta phi plot, And this is now native to the method. This is angular distribution, polar plot. Remember, 2 angles. Everybody else does it in science. You represent the data in polar coordinates with a color plot. Normal is 0. This is natural for the method. This is angular distribution. And then it is again, indeed, transparent physical, meaning it is intensity distribution on the emission sphere in 3-dimensional K-space. One has to...
Excuse me, you have 5 minutes together with questions. 5 minutes only.
Finally, if one scans another angles, one arrives to the 3-dimensional plot, and this 3-dimensional plot is what we call is measured in the spherical diff sector. And yes, so one can measure 3-dimensional Fermi surfaces with the A approach. If one concentrates on angles, then, and this is transparent physical, meaning so you can measure 3-dimensional Fermi surfaces and compare directly with DFT. How to measure true energy distribution? Again, very simple. One looks at our straightforward equations and one sees that if one keeps kinetic energy constant, one keeps momentum constant. So one needs to change this, and this can be changed by photon energy. It's a new method. I didn't try it myself, but we will certainly try. One keeps kinetic energy constant and measures theta phi plots as a function of h nu. And then one gets true energy distribution for every k point which you see, very transparent result. So it has to be measured the function of at a fixed kinetic energy, 3-dimensional Fermi surface, you fix E maximum Fermi energy, and then you arrive to 3-dimensional Fermi surface. So all natural, all is within the method, native to the method. One can come back to cylindrical symmetry and use the fisheye effect. So if you photograph with the fisheye lens, you can capture more, as in this nice example. So one could apply potential to the sample, increase angular acceptance, and everything remains cylindrical, data set spherical. You are in angle resolved for the emission spectroscopy. So one of the things which we were thinking would be good for the project, which is this workshop carries this name, would be a station which will allow it to do such data set. And I'm proud to show you that this is now existing in reality. So this is mini ARPES, which also can be taken to the synchrotron if one wants. But this is the ARPES system which concentrates on A approach and hopefully will make the method more transparent, more simple. And so this is our way to democratize ARPES, so to say. There is a simple analyzer and the system is now baked and is ready for, and we have even first data set which cannot be measured with the conventional analyzers just because of the problems I mentioned. This is a room temperature, bed vacuum, but you can already have very good map data. So at this point, I would like to thank you for your attention and to all my collaborators, of course.
Thank you. So now we have a time for probably 2 questions, so please.
Okay, I can.
Please.
Okay, maybe such just like a question, comment. So the first, you are speaking about KZ dependence, about 3-dimensional materials, right? But if we consider that we have small escape depths of the electrons, just like one layer, and you have everything KZ integrated. It is still then there is no problem actually. You could show this KZ integrated profiles, and it is exactly what people can get from calculations, right?
No, this is it's not so, because when people are talking about the ARPES and 2-dimensional materials, first of all, there are no exactly 2-dimensional materials because atom and its orbitals are essentially 3D objects. The second, and is very important for ARPES think, is that electron, which is living in the 2 dimensions, cannot be even seen in ARPES, because the photoelectron should get a recoil effect from 3D. Sorry?
I asked about three-dimensional. Why two-dimensional? I say
no,
two-dimensional.
But but electrons which we see in ARPES, they should get Kz momentum from the 3D lattice. So electrons should live in 3D lattice in order to get this collective recoil effect from this. So that's why you cannot live without 3 dimensions. That's why even one layer spectra, they look different for different photon energies. One could talk about the matrix elements, of course.
Even if it is Kz integrated over the whole brilliant zone in Kz.
This I don't understand. What do you mean Kz integrated?
If you have one layer and due to uncertainty principle, so
one layer is not a two-dimensional, strictly two-dimensional system. One
layer escape depth. Sergey, one layer escape depth is one layer. So you have Kz integrated.
Yeah, but you detect
three-dimensional, not two-dimensional. It's clear, but you have okay. It is a more difficult question.
Yes.
I just had another question.
Which have Kz component.
Okay, about that first part of the talk, this is iridium bismuth selenide. About this, you said it's perpendicular to momentum, but to what else? It should be also. What about this special points on tops and there are special points?
To all of them, yes, to all of them. So the material is great in the sense that it is to all of them. Any Fermi surface here, and this follows from these calculations. So it shows that perpendicular momentum is zero. So the spin is always perpendicular to the momentum of this reciprocal vector. So there is a point in K-space. There are 12 points in K-space, and the spin is always perpendicular to the vector.
But it's not defined. The direction is not defined. You should be it should be perpendicular to some plane.
No, it is always perpendicular to this momentum. This is what calculations show. This is what follows from this. As Z is the usual Z axis, and as parallel as perpendicular are always parallel to gamma m and perpendicular to gamma. This is very unique structure. That's why it is. This is very interesting.
So it's not defined at the top, at the bottom, and in the corners it is like a saddle point, and it is like a.
Wait. These points are symmetry equivalent. This is simple cubic structure. They are all the same. These are 12 points of this 3D structure, and they're all the same. They're all gamma m. A portion of gamma m. A portion of gamma m.
Okay.
Yo, thank you, Sergey. Let's end the speaker again.
Thank you.
Thank you.